Imagine standing on the edge of humanity's greatest frontier, looking up at a crimson sky that has witnessed secrets for billions of years. What if I told you that scattered across the rust-colored deserts of Mars, lying in wait beneath ancient dust and inside frozen valleys, there are discoveries so strange, so profoundly mysterious, that they challenge everything we thought we knew about our place in the universe? What if the red planet isn't just a barren wasteland, but a cosmic time capsule holding clues to questions we've been asking since we first looked up at the stars? Tonight, we're going to journey across millions of miles of space to explore 10 mind-blowing discoveries on Mars that have left scientists speechless, sparked heated debates in laboratories around the world, and opened doorways to possibilities that once belonged only to science fiction. Some of these findings suggest that Mars was once a world very much like Earth. Others hint at processes and phenomena we still can't fully explain. And a few have made even the most skeptical researchers pause and wonder if we're truly alone in this vast, indifferent cosmos. Before we begin, I want you to ask yourself something. When you look up at that reddish point of light in the night sky, what do you see? Just a dead rock floating in the darkness? Or do you see what it once was, what it might still hide, what it could tell us about our own world's past and future? Keep that question in your mind as we explore what rovers, orbiters, and decades of exploration have uncovered on this alien world. Let's start our journey with something that sounds simple but is utterly revolutionary. Water. Not the idea of water, not the theory of water, but actual, tangible evidence of water on Mars. And I'm not just talking about the distant past. In 2015, NASA made an announcement that sent shockwaves through the scientific community. Using data from the Mars Reconnaissance Orbiter, researchers confirmed that liquid water flows on Mars today, right now. As you listen to these words, there are seasonal streams of briny water trickling down Martian slopes during the warmer months. These recurring slope lineae, or RSL as scientists call them, appear as dark streaks that grow during warm seasons and fade when it gets cold. Think about that for a moment. We spent decades arguing about whether Mars ever had water, and now we know it has water in liquid form in the present day. But here's where it gets truly fascinating. Water on Mars shouldn't exist in liquid form. The atmospheric pressure is so low, less than 1% of Earth's, that water should instantly either freeze solid or evaporate into vapor. There's no comfortable middle ground. So how is liquid water flowing? The answer lies in salt. Perchlorates, highly concentrated salts in the Martian soil, lower the freezing point of water and allow it to remain liquid even in conditions that would be impossible otherwise. It's a harsh, briny solution that would be toxic to most Earth life as we know it, but it's water nonetheless. The implications shake the very foundation of how we search for life in the universe. For decades, astrobiologists have operated under a simple but powerful principle: follow the water. Wherever we find water, we find the potential for life. Every extreme environment on Earth where liquid water exists, from the crushing depths of the ocean to the scalding waters of hydrothermal vents, from the frozen lakes beneath Antarctic ice to the acid-drenched pools of volcanic calderas, we find life. Life finds a way. Life adapts. Life persists. So what does it mean that Mars has liquid water? NASA's Curiosity rover has made this question even more complex. Drilling into Martian rocks, it discovered that billions of years ago, Mars had bodies of water that weren't just fleeting or seasonal. We're talking about lakes that persisted for millions of years, perhaps tens of millions of years. Lakes with fresh water. Lakes with the right pH balance. Lakes with the right chemical composition. Lakes that, according to every metric we can measure, were habitable. Not just wet, but genuinely habitable. Picture this ancient Mars in your mind. Around 3.7 billion years ago, the same time life was taking hold on Earth, Mars had a thicker atmosphere, warmer temperatures, and a surface dotted with lakes and rivers. The Gale crater, where Curiosity now roams, wasn't a crater at all but a lake bed fed by rivers carrying sediment from mountains. The rover has found rounded pebbles, the kind that only form when water tumbles them smooth over long periods. It's found mudstones that could only form at the bottom of calm, persistent lakes. It's found mineral veins where water percolated through cracks in rocks, leaving chemical signatures of a wetter world. What happened to that world? Why did Mars transform from a potentially habitable planet into the frozen desert we see today? That's one of the great mysteries we're still unraveling. The leading theory suggests that Mars lost its magnetic field billions of years ago. Without that protective shield, solar wind stripped away the atmosphere over millions of years, reducing the atmospheric pressure until liquid water could no longer exist on the surface. The water didn't disappear entirely. Much of it is now locked in polar ice caps and underground ice deposits. Some of it was lost to space. And some, as those dark streaks remind us, still finds a way to flow. Here's a question for you to ponder. If Mars had habitable conditions for millions of years, the same amount of time it took for life to develop on Earth, could life have emerged there too? And if it did, what happened to it? Did it die out when the planet changed, leaving only fossils waiting to be discovered? Or did it adapt, retreating underground where water and protection from radiation still exist, evolving into forms we might not even recognize as life? Now, let's venture into our second discovery, one that has puzzled scientists and sparked countless debates. Methane. A simple molecule, 4 hydrogen atoms bonded to 1 carbon atom. But on Mars, it's anything but simple. On Earth, the vast majority of atmospheric methane comes from living organisms. Cows produce it. Wetlands produce it. Even termites produce it. Geological processes can create methane too, but biological sources dominate. So when the European Space Agency's Mars Express orbiter detected methane in the Martian atmosphere in 2004, and when NASA's Curiosity rover confirmed these readings years later with its own instruments, scientists faced a tantalizing mystery. Where is this methane coming from? Here's what makes Martian methane so baffling. The concentrations vary dramatically. Sometimes Curiosity detects background levels of about 0.7 parts per billion. Other times, the levels spike to 7 parts per billion or higher, a tenfold increase. Then they disappear again. Methane shouldn't behave this way on Mars. The molecule is destroyed by ultraviolet radiation in the Martian atmosphere, but this process should be gradual and steady, not wildly fluctuating. The spikes suggest something is actively releasing methane into the atmosphere, and doing so in irregular bursts. The possible explanations fall into 2 categories, and both are profound. The first is geological. Deep beneath the Martian surface, there could be ongoing chemical reactions between water and certain types of rock, a process called serpentinization, which produces methane. This would require liquid water underground, active chemistry, and pathways for the gas to reach the surface, perhaps through cracks or vents. It would mean Mars is more geologically active than we thought, with warm, wet environments hidden beneath the frozen surface. The second explanation is biological. Microorganisms called methanogens, which exist in numerous extreme environments on Earth, produce methane as a byproduct of their metabolism. If similar organisms exist in subsurface water deposits or soil on Mars, they could be releasing methane. The seasonal variations in methane levels could correspond to seasonal changes in microbial activity, just as we see on Earth where wetlands release more methane during warm seasons. NASA's Curiosity rover has added another wrinkle to this mystery. In 2019, the rover detected the largest methane spike ever measured on Mars. The reading was 21 parts per billion, 3 times higher than any previous detection. Then, just a day later, it vanished. The methane was simply gone, as if it had never been there. This sudden appearance and disappearance suggests a nearby source that released a plume of gas, which then quickly dispersed or was destroyed. Scientists have proposed that methane might be stored in ice structures called clathrates, where methane molecules are trapped in cages of water ice. When these structures are disturbed by temperature changes or geological activity, they could release sudden bursts of methane. But this is still speculation. We don't know for certain. The Trace Gas Orbiter, a spacecraft designed specifically to study Martian atmospheric gases, has added to the confusion. Its extremely sensitive instruments have sometimes failed to detect methane when and where it should be present based on Curiosity's surface measurements. How can a rover detect significant methane levels while an orbiter sees nothing? Some scientists suggest the methane releases are extremely localized and transient, appearing and disappearing so quickly that the orbiter misses them. Others wonder if there's something we don't understand about methane chemistry in the Martian environment. Ask yourself this: if microorganisms are producing methane on Mars right now, this very moment, what does that mean for our understanding of life in the universe? Would it mean life arose independently on two planets in the same solar system, suggesting life might be common throughout the cosmos? Or could life have transferred between Earth and Mars on meteorites, meaning we might all be Martians, descendants of organisms that started on the red planet and hitched a ride on a rock blasted into space by an ancient impact? Our third discovery takes us into even stranger territory: organic molecules, the building blocks of life as we know it. In 2018, NASA announced that Curiosity had found organic molecules in 3-billion-year-old sedimentary rocks in Gale Crater. These weren't simple molecules. The rover detected thiophene, benzene, toluene, and other complex organic compounds. When Curiosity heated rock samples in its onboard laboratory, these organic molecules were released, creating a chemical signature that left no doubt about their presence. Now, before we get carried away, we need to understand what this means and what it doesn't mean. Organic molecules are molecules containing carbon bonded to hydrogen, and often to other elements. They're called organic because they're associated with life on Earth, but they can also form through non-biological processes. Meteorites contain organic molecules. Chemical reactions in space create organic molecules. So finding them on Mars doesn't automatically mean we've found evidence of life. But, and this is crucial, it doesn't rule it out either. What makes this discovery so significant is the complexity and variety of the organic molecules, and the fact that they've survived for 3 billion years. These molecules were found in mudstone, rock that formed at the bottom of an ancient lake. The lake existed at a time when Mars had conditions suitable for life. The organic molecules could have come from ancient Martian life, or they could have been created by chemical reactions in the lake, or they could have been delivered by meteorites and preserved in the sediment. We simply don't know yet. Curiosity has also detected organic molecules in the Martian atmosphere. Seasonal variations in atmospheric organic compounds suggest active chemistry is happening somewhere on or beneath the surface. Some of these molecules break down and reform in cycles that correlate with the Martian seasons, hinting at ongoing processes we're only beginning to understand. The preservation of these ancient organic molecules tells us something important about Mars. Unlike Earth, where plate tectonics recycle the surface and biological activity reworks the chemistry, Mars has vast areas of ancient surface that have remained relatively undisturbed for billions of years. It's a geological time capsule. If life ever existed on Mars, if microorganisms ever swam in those ancient lakes or grew in films on wet rocks, the evidence might still be there, waiting in the right location, preserved in the right conditions. But there's a complication, and it's one that troubles researchers who are planning future missions. Curiosity's instruments detected chlorinated organic compounds, molecules where chlorine atoms have attached to organic molecules. This might be contamination in a sense, not from Earth, but from the Martian environment itself. Perchlorates, those same salts that allow liquid water to exist on Mars, can react with organic molecules when heated, potentially destroying evidence of complex organics or creating misleading signals. The very process of analyzing Martian samples might be altering what we're trying to find. It's like trying to read an ancient document that fades when you shine light on it. We have to be extraordinarily careful in how we look. The European Space Agency's Rosalind Franklin rover, scheduled to launch in the coming years, will drill 2 meters below the Martian surface, deeper than any previous mission. At those depths, organic molecules would be better protected from radiation and oxidation. If there's evidence of past life on Mars, that might be where we'll find it. Consider this question. How would you feel if we discovered that organic molecules on Mars were definitely biological in origin, but from microorganisms that died billions of years ago? Would you be excited that life once existed beyond Earth? Or disappointed that we missed it by eons? That we're exploring a graveyard of a once-living world? Our fourth discovery is one that captures the imagination like few others, even though it's been thoroughly explained by science. The face on Mars. In 1976, NASA's Viking 1 orbiter photographed a region of Mars called Cydonia. Among the mesas and rocky terrain, one formation stood out. In the low-resolution image, it looked remarkably like a humanoid face staring up from the Martian surface, as if some ancient civilization had carved a monument into the rock. The image was released to the public, and it ignited a firestorm of speculation that persists to this day. Was it an alien monument? Evidence of an ancient Martian civilization? A message left for future explorers? The face seemed to have eyes, a nose, a mouth, all in proportions that struck the human brain as familiar and intentional. Some researchers, particularly those outside mainstream science, began looking for other structures in the Cydonia region. They claimed to find pyramids, geometric arrangements, even a city. Books were written. Documentaries were made. The face on Mars became a cultural phenomenon. NASA maintained that it was simply a mesa, a flat-topped hill, and that the appearance of a face was due to pareidolia, the psychological phenomenon where the human brain perceives familiar patterns, especially faces, in random or ambiguous stimuli. It's the same reason we see shapes in clouds or faces on the moon. Our brains are hardwired to recognize faces, a survival mechanism that helped our ancestors quickly identify friend from foe, and this wiring sometimes fires when no face is actually there. The debate raged for decades, but it was settled definitively when better images became available. In 1998, Mars Global Surveyor captured higher-resolution images of the face. In 2001, it photographed the formation again with even better cameras, showing details as small as 1.5 meters across. In 2007, the Mars Reconnaissance Orbiter, with its phenomenally powerful high-rise camera, captured images with resolution down to mere centimeters. These images revealed the truth. The face is indeed just a mesa, eroded by wind and ancient water. The features that look like eyes, nose, and mouth are simply irregularities in the rock, shadows and highlights that in the right lighting and the right angle created the illusion of a face. In different lighting, from different angles, it looks nothing like a face at all. It's a perfectly natural geological formation, no more unusual than thousands of other mesas and buttes on Mars. But here's what's fascinating about the face on Mars, even though it's not artificial. It tells us something profound about human nature and our desire to find meaning in the cosmos. We want to find evidence of other civilizations. We want to know we're not alone. This desire is so strong that we'll see faces on other planets, construct elaborate theories, and passionately defend them even when evidence contradicts them. The face on Mars also reminds us why rigorous scientific methodology is so important. Initial impressions can be deceiving. Low-quality data can lead to incorrect conclusions. We need better instruments, multiple observations, careful analysis, and the willingness to change our minds when better evidence becomes available. The same scientific process that debunked the face on Mars is the process that will, if the evidence exists, eventually confirm the presence of life on Mars or evidence of past life. Yet there's something poetic about the whole episode. For a brief moment in history, millions of people looked at that image and wondered. They imagined ancient Martians carving monuments. They dreamed of making contact with another intelligence. The face was ultimately a case of mistaken identity, but the yearning it represented, the hope it embodied, that's very real and very human. Think about this. Why are we so drawn to the idea of finding artificial structures or evidence of intelligence on Mars? Is it because discovering that we're truly alone in the universe is more frightening than finding out we have neighbors, even if they're long extinct? What would it mean for humanity's sense of purpose if we confirmed that in all the billions of years Mars existed, in all the millions of years it had habitable conditions, life never arose at all? Now let's turn to our fifth discovery, one that's both beautiful and scientifically significant. Blueberries on Mars. Not actual berries, of course, but small, spherical formations of hematite that NASA's Opportunity rover found scattered across the Martian surface like blueberries across a muffin. When Opportunity landed in Meridiani Planum in 2004, it almost immediately encountered these small spheres, about the size of BBs, embedded in rocks and scattered on the ground. Initial analysis revealed they were made of hematite, an iron oxide mineral. On Earth, hematite concretions, small spherical formations of the mineral, typically form in one of two ways. They can precipitate out of water that's percolating through rock, or they can form from volcanic activity. The question was, which process created the Martian blueberries? The answer turned out to be water. These concretions formed billions of years ago when water, rich in dissolved iron, moved through porous rock. As the chemical conditions changed, the iron precipitated out, slowly building up in spherical formations around tiny nuclei. This process takes time, and lots of water. The sheer abundance of these blueberries scattered across the plains of Meridiani suggested that water was present in the rock for extended periods, perhaps millions of years. This discovery was crucial in confirming that ancient Mars had abundant water, and not just surface water. The blueberries indicated that water permeated underground, flowing through aquifers and saturating the soil. This subsurface water would have been protected from the thin atmosphere, from radiation, from the temperature extremes of the surface. If life existed on ancient Mars, these water-saturated rock formations would have been ideal habitats. Opportunity found another fascinating detail. The blueberries were harder and more resistant to erosion than the surrounding rock, so as the softer rock eroded away over billions of years, the blueberries were left behind, accumulating on the surface. Some areas were so densely covered with them that it looked like someone had scattered ball bearings across the landscape. The rover's wheels crunched over them, and its cameras captured images of them embedded in rocks like raisins in a cake. But the story gets more intriguing. More recent analysis has revealed that Mars has different types of spherules, not all of which are blueberries. Some spherules found by the rovers appear to have different compositions and possibly different origins. Some might have formed from volcanic processes. Others might have been created by meteorite impacts, where the heat and pressure of the impact melted and reformed rock into spherical shapes. The diversity of these formations tells us that Mars has had a complex geological history with multiple processes shaping its surface. Scientists have even found that studying Martian blueberries helps us understand similar formations on Earth. In Utah, there are hematite concretions remarkably similar to the ones on Mars, and they become a testing ground for understanding the Martian versions. By studying how water created these formations on Earth, we can better interpret what the Martian blueberries tell us about ancient water on the red planet. Here's something to consider. These tiny spheres have been sitting on Mars for billions of years, witnesses to the planet's transformation from a warm, wet world to a frozen desert. If you could hold one in your hand, you'd be touching something that formed when life on Earth was just beginning, when our planet was covered in microbial mats and the first photosynthetic organisms were starting to change our atmosphere. What stories could those blueberries tell if they could speak? Our sixth discovery ventures into the realm of the genuinely mysterious, phenomena that we've observed but don't fully understand. Strange lights and flashes on Mars. Over the decades of Martian observation, both from orbit and from the surface, there have been numerous reports of unexplained bright spots, flashes, and lights. Before you get too excited about alien civilizations, most of these have prosaic explanations. Cosmic rays striking camera sensors, reflections from shiny mineral surfaces, data transmission errors, and instrumental glitches can all create apparent light sources that aren't really there. But some observations have been harder to explain. In 2014, Curiosity rover captured an image that showed a bright spot on the horizon, a spike of light reaching up from the surface. The image went viral, spawning theories about alien bases, underground civilizations, and secret human colonies on Mars. NASA's explanation was more mundane but still interesting. The light was likely caused by sunlight reflecting off a shiny rock surface or glinting off the rover itself, or it could have been a cosmic ray strike on the camera sensor. Given that Curiosity takes thousands of images and cosmic rays are constantly bombarding Mars, occasional strange artifacts in images are inevitable. But there's another phenomenon that's more intriguing. Transient lights and bright spots have been observed from Earth-based telescopes for centuries. Astronomers in the 1800s and 1900s reported seeing flashes and bright spots on the Martian surface. Most of these were attributed to observational errors, atmospheric distortion, or wishful thinking. But in the modern era, with better instruments, some observations remain puzzling. One theory involves electrostatic discharges. Mars experiences massive dust storms, some so large they engulf the entire planet. When countless tiny dust particles collide at high speeds, they can build up electric charges, similar to how rubbing a balloon on your hair creates static electricity. On Earth, we see this in thunderstorms, where colliding ice particles and clouds build up charges that eventually discharge as lightning. Could Martian dust storms create lightning, producing bright flashes? For years, this was theoretical because no one had definitively detected lightning on Mars. The Martian atmosphere is so thin that lightning as we know it shouldn't easily occur. But in 2006, during a massive dust storm, instruments detected what appeared to be electrical activity. Whether this was true lightning or some other form of discharge remains debated. The evidence is tantalizing but not conclusive. There's another possible explanation for some light phenomena. Meteorites. Mars has a thinner atmosphere than Earth, so smaller meteorites that would burn up harmlessly over our planet can reach the Martian surface. When these meteorites streak through the Martian atmosphere, they create bright trails. When they impact the surface, they can create flashes. Orbiting spacecraft and rovers have captured numerous new impact craters on Mars, appearing in areas that were crater-free just years before, confirming that Mars is constantly being bombarded by space rocks. The Mars Reconnaissance Orbiter has even managed to capture images of meteorites in the act of creating new craters, correlating bright flashes observed by other instruments with the appearance of fresh impact sites. It's a reminder that planetary surfaces are dynamic, constantly being reshaped by ongoing processes. The Mars Reconnaissance Orbiter has even managed to capture images of meteorites in the act of creating new craters, correlating bright flashes observed by other instruments with the appearance of fresh impact sites. It's a reminder that planetary surfaces are dynamic, constantly being reshaped by ongoing processes. Here's a question that might unsettle you. If bright flashes on Mars are mostly from natural causes like meteor impacts, cosmic rays, and dust storms, does that explain all of them? Or could there be phenomena occurring on Mars that we simply don't have the right instruments to detect or the right theories to explain? How much do we really understand about the complex interactions between solar wind, cosmic rays, dust, and the Martian environment? Our seventh discovery brings us to something that seems impossible but is undeniably real. Snow on Mars. Not just ice, but actual precipitation falling from Martian skies. Mars has weather. This might seem obvious given that it has an atmosphere, but the weather on Mars is radically different from anything on Earth. The Martian atmosphere is 95% carbon dioxide, incredibly thin and incredibly cold. Average temperatures hover around -80 degrees Fahrenheit, with highs barely reaching above freezing in some locations during summer. But Mars has clouds. Wispy clouds made of water ice form in the Martian atmosphere, particularly around the polar regions and at high altitudes. The Phoenix lander, which touched down near Mars' North Polar region in 2008, detected snow falling from these clouds. The snow was made of water ice, delicate crystals falling from clouds about 4 kilometers high. However, due to the thin atmosphere and low humidity, the snow sublimated, turning from solid directly to vapor before reaching the ground. It was a ghostly snowfall, disappearing before it could settle. But that's not the only type of Martian snow. The Mars Reconnaissance Orbiter has detected carbon dioxide snow falling from clouds at the South Polar region. This is something that doesn't occur naturally anywhere on Earth. Carbon dioxide freezes at much lower temperatures than water, and the conditions have to be exactly right. These carbon dioxide snowflakes fall and actually reach the ground, contributing to the polar ice cap. The Martian polar ice caps are themselves fascinating structures, layered compositions of water ice and carbon dioxide ice. During the Martian winter, which lasts about 6 months in each hemisphere, carbon dioxide from the atmosphere freezes out and falls as dry ice snow, building up a seasonal cap over the permanent water ice cap. In spring and summer, this carbon dioxide sublimates back into the atmosphere, shrinking the polar cap. It's a seasonal cycle like nothing else in our solar system. These polar regions undergo other strange transformations. As the dry ice sublimates in spring, it doesn't melt evenly. Gas trapped beneath the ice can build up pressure and suddenly burst through, creating geysers of carbon dioxide gas and dust that shoot up to hundreds of feet in the air. These geysers carve dark streaks across the ice as they spray dust and sand onto the surface. From orbit, these dark streaks look almost biological, like mold spreading across the ice, and they change and grow over the course of weeks. They're not biological, but they're a dramatic reminder that Mars is an active world with dynamic processes. The Martian atmosphere also produces dust devils, towering vortices of wind and dust that spiral across the surface. These aren't rare events. Rovers have photographed hundreds of dust devils, some towering 10 kilometers high, dwarfing any tornado on Earth. The Spirit and Opportunity rovers both benefited from dust devils that swept across their solar panels, cleaning off accumulated dust and extending their missions by years. It was as if Mars itself was helping the rovers survive. And then there are the planet-wide dust storms, phenomena that occur roughly every few Martian years. These storms can start small, localized dust clouds, but under the right conditions, they grow. The dust absorbs sunlight, heating the atmosphere, which creates stronger winds, which lifts more dust, which absorbs more sunlight, creating a runaway feedback loop. Within weeks, the entire planet can be shrouded in a thick haze of dust that blocks out the sun. The 2018 global dust storm was particularly severe. It covered the entire planet and blocked so much sunlight that NASA's Opportunity rover, which relied on solar panels for power, couldn't charge its batteries. The rover went into hibernation, and despite months of attempts to re-establish contact, it never woke up. The storm had finally ended the mission of a rover that had operated for nearly 15 years, exploring Mars far longer than anyone anticipated. It was a poignant reminder that Mars, for all its similarities to Earth, is a harsh and unforgiving world. Think about this. If human explorers live on Mars someday, they'll experience seasons of darkness when dust storms block out the sun for weeks or months. They'll watch carbon dioxide snow fall from pink skies. They'll need to take shelter from dust devils that could sandblast equipment and habitats. Does this sound like a world we could ever truly call home? Or will Mars always be a place where humans are visitors, perpetually dependent on technology for survival? Our 8th discovery takes us deep beneath the Martian surface to something that could revolutionize our search for life. Lakes under the ice. In 2018, scientists analyzing data from the Mars Express Orbiter's Marcy's radar instrument announced a stunning discovery. Beneath the South Polar ice cap, about 1.5 kilometers below the surface, the radar detected a bright reflection consistent with a body of liquid water about 20 kilometers across. This wasn't a seasonal puddle or a thin film of brine. This appeared to be a stable lake of liquid water existing in the present day beneath the Martian ice. How is this possible? The temperature at the Martian South Pole is far too cold for pure water to remain liquid. But just as perchlorates allow thin films of brine to flow on the surface, dissolved salts could keep water liquid beneath the ice. The pressure from the ice cap above, the insulating effect of the ice, and the salt content could combine to create conditions where a briny lake persists despite the freezing temperatures. The discovery was met with both excitement and skepticism. Skeptics pointed out that radar data can be ambiguous. Other materials or geological features might create similar bright reflections. The lake interpretation, while plausible, wasn't definitive. Science demands extraordinary evidence for extraordinary claims, and a radar signature alone might not be enough. But in 2020, the same research team announced they'd found not just one but multiple bright spots beneath the South Polar ice. 3 additional bodies of water, smaller than the main one but with similar radar signatures, appeared to exist in the region. This multiplicity was compelling. If one bright spot might be a misinterpretation, finding multiple signatures in the same region strengthened the case that we were really seeing liquid water. If these subsurface lakes exist, they could be among the most important discoveries in planetary science. On Earth, life exists in subglacial lakes beneath Antarctic ice. Lake Vostok, buried under 4 kilometers of ice, has been isolated from the surface for millions of years, yet it contains microbial life. The organisms there survive in complete darkness, in frigid temperatures, cut off from the outside world. If life can exist in Lake Vostok, could it exist in a Martian subglacial lake? There are challenges, of course. The Martian lakes, if they exist, would be extremely salty, far saltier than Earth's oceans. They'd be far colder than most Earth environments, likely around -10 to -30 degrees Celsius. They'd be under immense pressure from the ice above. There would be no photosynthesis, no light, no oxygen. Any life there would have to be chemosynthetic, deriving energy from chemical reactions rather than sunlight, similar to the organisms living around hydrothermal vents on Earth's ocean floor. But here's what's tantalizing. If life exists in these lakes, it would be completely isolated from the surface, protected from radiation, from the oxidizing surface environment, from the temperature extremes. It could have survived there for billions of years, even as the surface transformed into a frozen desert. We could drill through the ice and discover an entire biosphere that evolved separately from anything on Earth. A second genesis, proof that life arises wherever conditions permit. Of course, we're not ready to drill into Martian subglacial lakes yet. The technology required is formidable. We'd need to ensure we don't contaminate the lake with Earth microbes, something that's proven challenging even for Antarctic drilling projects. We'd need rovers and instruments capable of operating in extreme cold and pressure. We'd need to develop techniques for analyzing samples in situ or preserving them for return to Earth. But if those lakes are there, they represent one of the most compelling targets in our search for life beyond Earth. Ask yourself this. If we discovered microbial life in a Martian subglacial lake, and DNA analysis showed it was related to Earth life, suggesting panspermia, the transfer of life between planets, would that be more or less profound than discovering life that arose completely independently? What would it mean if Earth and Mars shared a common tree of life, if we were, in some sense, one biosphere split between 2 worlds? Our 9th discovery is one that challenges our understanding of planetary geology and raises profound questions about Mars' past. Evidence of ancient plate tectonics. On Earth, plate tectonics is the fundamental geological process that shapes our planet. The crust is broken into massive plates that float on the mantle, moving slowly over millions of years. Where plates collide, mountains rise. Where they pull apart, oceans form. Plate tectonics recycles the crust, drives volcanic activity, creates earthquakes, and may even be essential for life by regulating the atmosphere and climate through the carbon cycle. Mars shows no evidence of plate tectonics today. The crust appears to be a single solid shell, not broken into moving plates. This difference has profound implications. Without plate tectonics, Mars couldn't recycle its crust, couldn't regulate its atmosphere long-term, and lost one of the mechanisms that might have kept it geologically active and habitable. But recent analysis of Martian geology suggests this wasn't always the case. In the Valles Marineris region, a massive canyon system that dwarfs Earth's Grand Canyon, researchers have found fracture patterns, fault lines, and geological structures that look remarkably similar to plate boundaries on Earth. Some regions of Mars show signs of crustal compression and extension, of blocks of crust moving relative to each other, of volcanic activity associated with what could be ancient plate boundaries. In 2020, a study analyzing the chemistry and topography of the Martian northern lowlands proposed that plate tectonics might have operated on Mars in the distant past, perhaps 4 billion years ago, before shutting down as the planet cooled and its interior solidified. If true, this would mean that for a brief period in its early history, Mars was even more Earth-like than we realized, with a dynamic surface, active geology, and possibly a magnetic field generated by a convecting core. Why would Martian plate tectonics stop? The most likely explanation involves size. Mars is about half the diameter of Earth and has only about 10% of Earth's mass. Smaller planets cool faster. The interior heat that drives geological activity dissipates more quickly. Within a billion years or so of Mars formation, it may have cooled enough that its mantle stopped convecting vigorously, plate tectonics ceased, and the crust froze into a single immobile shell. This shutdown had cascading consequences. Without plate tectonics, Mars lost its magnetic field as the core stopped generating a dynamo. Without a magnetic field, solar wind stripped away the atmosphere. Without a thick atmosphere, liquid water couldn't exist on the surface. Without liquid water, any surface life would have perished or retreated underground. The death of plate tectonics may have triggered the death of habitable Mars. But there's a counter-argument. Some scientists point out that the evidence for Martian plate tectonics is circumstantial and that other processes could explain the observed geological features. Impact basins, volcanic activity, and thermal expansion and contraction of the crust could create fractures and faults without requiring plate tectonics. The debate is ongoing, and like many questions about Mars, we need more data to settle it definitively. What we do know is that Mars has a dramatic hemispheric dichotomy, something unique in the solar system. The northern hemisphere is mostly smooth lowlands, while the southern hemisphere is rough, cratered highlands, elevated several kilometers above the north. This division is sharp, almost as if someone drew a line around the planet. Various theories attempt to explain this. Perhaps a massive impact in the early solar system blasted away much of the northern crust. Perhaps ancient plate tectonics created the division. Perhaps mantle convection patterns led to different crustal formation in the north and south. We don't know for certain, but understanding this dichotomy is crucial to understanding Mars' history. Here's something to ponder. If Mars once had plate tectonics and lost it, could a planet regain plate tectonics? Could human activity, introducing heat into the Martian interior or altering surface conditions, somehow restart geological processes? Or is the death of a planet's geology irreversible, a one-way journey from active world to frozen museum? Our 10th and final discovery is perhaps the most consequential for humanity's future. Resources that could support human exploration and settlement. Mars isn't just a scientific curiosity. It's a potential future home, and understanding what resources are available there is crucial. We've already discussed water ice, which exists in abundance in the polar caps and underground ice deposits. Recent discoveries suggest that there are massive deposits of water ice just beneath the surface at mid-latitudes, accessible to robotic drills or even to astronauts with shovels. The Mars Reconnaissance Orbiter has found locations where meteorite impacts or cliff erosion has exposed underground ice, revealing deposits that are meters thick and remarkably pure. For future Mars explorers, this ice represents not just drinking water but oxygen to breathe and hydrogen for rocket fuel. Water can be split into hydrogen and oxygen through electrolysis, providing life support and enabling the production of rocket propellant on Mars for the return journey to Earth. The Martian soil itself contains resources. The perchlorates that we've mentioned multiple times are problematic for life but useful for industry. Perchlorates contain oxygen that can be extracted. The iron-rich Martian soil could be processed for construction materials. The regolith can be sintered or melted using microwaves or solar furnaces to create bricks and building materials for habitats. NASA's MOXIE experiment, carried aboard the Perseverance rover, has successfully demonstrated that oxygen can be extracted from the Martian atmosphere. MOXIE takes in carbon dioxide, which makes up 95% of the Martian air, and uses a chemical process to split it into oxygen and carbon monoxide. It's a small demonstration unit, but it's proven the concept works. A scaled-up version could produce enough oxygen for breathing and for rocket oxidizer, making Mars missions significantly more feasible by reducing the amount of supplies that need to be brought from Earth. The Martian environment also offers solar energy, particularly near the equator where solar panels can generate electricity, albeit less efficiently than on Earth due to the greater distance from the Sun and occasional dust on the panels. Wind energy is less practical because the thin atmosphere means Martian winds, even the strong ones, have relatively little force. Nuclear power, likely in the form of small modular reactors or radioisotope generators, will probably be essential for any long-term human presence, providing reliable power regardless of dust storms or polar night. Mars has minerals and ores. Rovers have detected a variety of minerals, including clays, sulfates, and various iron oxides. While we haven't conducted detailed mineral surveys like we would for a mining operation, orbital observations and rover data suggest that Mars has mineral diversity that could, in principle, support industry. Whether it's economically feasible to mine and process Martian materials is another question, but the raw materials appear to exist. The Martian gravity, about 38% of Earth's, is both a challenge and an opportunity. It's low enough that launching rockets from Mars requires far less fuel than launching from Earth, making Mars a potential staging point for missions to the asteroid belt or outer solar system. But it's high enough that it might mitigate some of the health problems associated with zero gravity, such as bone density loss and muscle atrophy, though we won't know for certain until humans spend extended time there. One of the most intriguing proposals for Mars involves terraforming, transforming the planet's environment to make it more Earth-like. This is speculative and far beyond current technology, but it's worth considering. The basic idea is to thicken the atmosphere, raise the temperature, and potentially allow liquid water to exist on the surface again. Various methods have been proposed. We could release greenhouse gases to trap heat, perhaps by vaporizing the polar ice caps or importing ammonia-rich asteroids. We could use mirrors in orbit to reflect sunlight onto the poles, warming them and releasing carbon dioxide. We could engineer microorganisms to produce greenhouse gases or process Martian soil. However, more recent analysis suggests terraforming Mars may be harder than once thought. Studies indicate that Mars doesn't have enough accessible carbon dioxide to create a thick atmosphere through any realistic process. Even if we vaporized all the polar ice and all the carbon dioxide in the soil and rocks, we might only achieve an atmosphere a fraction of Earth's pressure. Terraforming might require importing vast quantities of gases from elsewhere in the solar system, a project of almost incomprehensible scale and duration. But even without full terraforming, Mars could support human presence. Habitats would need to be pressurized and protected from radiation, probably built underground or under regolith for shielding. Humans would wear spacesuits outside. Food would be grown in pressurized greenhouses. It wouldn't be easy or comfortable, but it would be possible with technology we can envision developing in the coming decades. Why go to Mars at all? This question gets to the heart of human nature. We explore because we're curious. We explore because we're driven to understand our place in the universe. We explore because staying on one planet makes humanity vulnerable to existential risks like asteroid impacts or civilizational collapse. We explore because the challenges of living on Mars will drive innovation that benefits Earth. We explore because there are questions on Mars that can only be answered by going there. Think about what it would mean to stand on Mars, to be the first human to set foot on another planet. You'd look up at a butterscotch sky, see the sun as a smaller, dimmer disk than on Earth, watch the twin moons Phobos and Deimos race across the sky, and know that beneath your feet might be evidence of life beyond Earth, or at least the story of why life never arose, which is equally profound. You'd be part of the lineage of exploration that took our ancestors out of Africa, across oceans, to the poles, and now to other worlds. You'd be writing a new chapter in the human story. But let me ask you something more challenging. Should we go to Mars? If there's even a possibility of microbial life existing in the soil or in subsurface ice, do we have the right to risk contaminating it with Earth organisms? Should we treat Mars as a pristine scientific preserve, or as a resource and potential home for humanity? These aren't easy questions, and they're ones we need to grapple with as we develop the capability to reach the red planet. As we come to the end of our journey across the rust-colored deserts and ancient river valleys of Mars, let's reflect on what we've discovered. We've found a world that once had conditions remarkably similar to early Earth, with lakes, rivers, and possibly oceans. We've found that water still exists there, both as ice and in briny flows. We've detected methane that could indicate geological activity or even life. We've found organic molecules, the building blocks of life, preserved in ancient rocks. We've seen how our minds can trick us into seeing faces and patterns, and we've learned to look more carefully, with better instruments and more rigorous methods. We've discovered geological wonders from blueberries of hematite to planet-wide dust storms, from carbon dioxide snow to possible lakes beneath the ice. We've found evidence that might point to ancient plate tectonics and a more dynamic past. And we've identified resources that could one day support human explorers and perhaps even settlers. But perhaps the most important discovery is this: Mars is not just a dead rock. It's a complex world with ongoing processes, with mysteries we're only beginning to unravel, with questions that challenge our understanding of planets, life, and our place in the cosmos. Every answer we find raises new questions. Every mystery we solve reveals deeper puzzles. We're living in an extraordinary time. Right now, there are multiple rovers on Mars, driving across its surface, analyzing rocks, searching for signs of past life. There are orbiters circling overhead, mapping the surface, studying the atmosphere, finding new targets for exploration. Space agencies and private companies are developing the rockets, habitats, and technologies that could send humans to Mars within the next couple of decades. The generation alive today might witness humanity becoming a two-planet species. But Mars also serves as a warning. It's a planet that had everything needed for life, that might have actually hosted life, but that lost its habitability. Its atmosphere was stripped away. Its water was lost or locked in ice. Its magnetic field died. The warm, wet world transformed into a frozen desert. If it can happen to Mars, could it happen to Earth? What does Mars teach us about the fragility of planetary habitability, about the delicate balance of processes that keep our world alive? There's a concept in planetary science called the habitable zone, the range of distances from a star where liquid water can exist on a planet's surface. Earth sits comfortably in the Sun's habitable zone. Mars is on the outer edge, receiving less sunlight, cooler, on the border of habitability. But the history of Mars teaches us that being in the habitable zone isn't enough. A planet needs the right mass to hold onto its atmosphere. It needs geological activity to recycle its crust and regulate its climate. It needs a magnetic field to protect against solar wind. It needs a complex interplay of factors that we're only beginning to understand. Mars had some of these factors, but not all, or not for long enough, and it died. This makes Earth seem more precious, doesn't it? Our planet isn't just habitable by accident. It's the right size, the right distance from the Sun, with the right moon to stabilize its axis, with plate tectonics and a magnetic field, with oceans and an atmosphere, with life itself that has transformed the environment and helped maintain habitability for billions of years. We live on a rare jewel, and Mars, our nearest neighbor, shows us what happens when a planet loses what makes it livable. Yet Mars also represents hope. Hope that life might arise wherever conditions permit, meaning the universe could be teeming with biology. Hope that we can learn from Mars' past to protect Earth's future. Hope that humanity's future isn't confined to one world, that we have options, that we can adapt and survive on other planets. Hope that the story of Mars isn't over, that the next chapter might be written by human explorers who land on its surface, establish research stations, and perhaps one day, cities. Imagine what future discoveries await. The Mars Sample Return mission, currently in development, plans to bring Martian rocks and soil back to Earth for analysis in sophisticated laboratories. Those samples might contain definitive evidence of past life, or compelling clues about Martian chemistry and geology that we can't fully analyze with rovers alone. The Rosalind Franklin rover will drill deep beneath the surface, reaching pristine samples protected from radiation and oxidation. Future missions might explore the polar ice caps, drill into subsurface ice, or even visit those potential subglacial lakes. Each mission will answer old questions and pose new ones. And then there's the human element. When astronauts finally set foot on Mars, what will they find? Will they discover something that rovers missed? Some subtle sign or unexpected phenomenon? Will they bring the flexibility and intuition of human observers to complement the precision and endurance of robotic explorers? Will they make the discovery that finally answers whether life exists or ever existed on Mars? Let me leave you with some final questions to ponder. Questions that don't have easy answers, but that are worth contemplating as you look up at that reddish point of light in the night sky. If we find fossilized microorganisms in Martian rocks, preserved from billions of years ago, how will that change your perspective on life in the universe? Will it make you feel less alone, or more aware of how rare and precious living worlds are? If we discover that Mars had all the ingredients for life but life never arose there, what does that tell us about the origin of life? Is life incredibly unlikely, a cosmic fluke that happened on Earth but nowhere else nearby? Or were the conditions on Mars just slightly wrong, missing some crucial ingredient we haven't identified yet? If we find living microorganisms in the Martian soil or ice, organisms that evolved completely independently from Earth life, representing a second genesis, how would that reshape your understanding of biology, evolution, and the possibilities for life throughout the cosmos? Should humanity make the enormous investment required to send people to Mars, or should we focus on robotic exploration and addressing challenges here on Earth? Can we do both? Should we do both? If we develop the technology to terraform Mars, to transform it into a more Earth-like world with breathable atmosphere and liquid water on the surface, should we do it? Or should we preserve Mars as it is, a natural laboratory and a monument to planetary evolution? What responsibilities do we have to potential Martian life? Should we treat Mars the way we should have treated pristine environments on Earth, with careful protection and minimal disturbance? Or is the potential benefit to humanity worth the risk of contamination? When the first human speaks from the surface of Mars, when we watch the video of that first footstep on another planet, how will it feel? Will it be a moment of triumph, of pride, of hope? Or will it be tinged with anxiety about the challenges ahead and the enormous investment required? And finally, what would you ask Mars if you could? If the planet could tell you its secrets, reveal what happened to it, show you what life it harbored or why life never arose, explain where all the water went and whether anything still lives in the deep subsurface, what would you want to know most? These are the questions that drive us to explore. These are the mysteries that make Mars so compelling. It's not just a scientific target or a potential resource. It's a world with a story that intersects with our own, that teaches us about planetary evolution and the conditions for life, that challenges us to expand our horizons and become something more than a single planet species. The 10 discoveries we've explored tonight, from water and methane to organic molecules, from the face that wasn't a face to blueberries of hematite, from mysterious lights to snow falling from alien skies, from hidden lakes to ancient plate tectonics, from resources for future explorers to the very possibility of life itself, these aren't endpoints. They're beginnings. Each discovery opens new avenues of inquiry, suggests new missions, raises new possibilities. Mars has captured human imagination for millennia. Ancient civilizations saw it as a wandering red star and named it after gods of war. Early astronomers peered through telescopes and thought they saw canals, evidence of an advanced civilization desperately channeling water across a dying world. Science fiction writers populated it with Martians of every description, from Wells' malevolent invaders to Bradbury's poetic ancient race. For generations, Mars represented the other, the alien, the mysterious neighbor that might harbor life or the ruins of lost civilizations. Now, in the early 21st century, we know Mars better than any previous generation. We've mapped its surface in exquisite detail. We've analyzed its rocks and soil. We've studied its atmosphere and weather. We've found organic molecules and flowing water. We've seen it not through distorting atmospheres or blurry telescopes, but through the eyes of rovers driving across its surface and orbiters swooping low overhead. The Mars of our imagination has been replaced by the Mars of reality, and remarkably, reality is just as compelling as fiction. The red planet that once represented alien invasion and science fiction fantasy now represents human aspiration and scientific discovery. It's where we'll test our technology and our courage. It's where we might find life beyond Earth or learn why life is rare. It's where we'll learn to live on another world, to extract resources, to build habitats, to survive in an environment that's hostile but not impossibly so. It's humanity's next frontier, calling to us across millions of miles of space with the promise of discovery and the challenge of exploration. As you go about your life on this blue world, remember that there's a red world out there with secrets still to reveal. Remember that robots are exploring it right now, this very moment, drilling into rocks, analyzing soil, searching for answers. Remember that engineers and scientists are designing the missions that will return samples to Earth, that will send humans to Mars, that will help us understand our neighboring world. Remember that the questions Mars poses about life, about planetary evolution, about our future as a spacefaring civilization, are among the most profound questions we can ask. And the next time you look up at Mars in the night sky, that steady red gleam among the stars, think about what might be there. Think about the ancient lakes now dry, the rivers now dust, the water now ice. Think about the methane seeping from somewhere, the organic molecules waiting in rocks, the possible microorganisms in subsurface ice. Think about the human footprints that might one day mark its dust, the first words spoken from another planet, the settlements that might arise in the craters and valleys. Mars is waiting. It's been waiting for billions of years, patient and silent, holding its secrets. We're only beginning to read its story, to understand its past, to imagine its future. The 10 mind-blowing discoveries we've explored are just the opening chapters. The rest of the story is yet to be written, and we're the ones who will write it. What will we find when we dig deeper, drill further, search harder? What mysteries still lie hidden in the Martian soil, beneath the polar ice, in the chemistry of the atmosphere? What will future rovers discover that will make today's findings seem preliminary? What will human explorers, with their flexibility and intuition, reveal that our robots missed? We don't know yet. That's what makes it exciting. That's what makes Mars the most compelling destination in our solar system. It's close enough to reach with technology we have or can develop soon. It's Earth-like enough that we can imagine living there. It's different enough that it challenges us and teaches us. It had water, it had organic molecules, it had habitable conditions. It might have had life. It might still have life hidden away somewhere, and it might one day have us. The journey to understanding Mars is the journey to understanding ourselves. It's about asking where we come from, whether we're alone, and where we're going. It's about pushing boundaries and satisfying that fundamental human drive to explore, to discover, to know. It's about ensuring that humanity has a future that extends beyond one planet, one cradle, one home. Mars is more than a destination. It's a mirror showing us what Earth could become if we're not careful. It's a laboratory teaching us how planets live and die. It's a challenge testing our technology and resolve. It's a mystery offering clues about life in the universe. It's a frontier promising adventure and discovery. It's a neighbor we're only now getting to know, finding it far stranger and more wonderful than we imagined. 10 mind-blowing discoveries, but countless mysteries remain. That's where you come in. Your generation might be the one that answers the question of life on Mars. You might witness the first human landing on another planet. You might see the establishment of the first permanent human settlement beyond Earth. You might be part of the team that makes the next great discovery, the one that rewrites textbooks and changes how we see the universe. Or perhaps the greatest discovery is yet to come, something we haven't even thought to look for, hiding in plain sight on the Martian surface or deep beneath it. Perhaps Mars is still keeping its best secrets, waiting for the right question, the right instrument, the right explorer to reveal them. That's the beauty of exploration. We don't know what we'll find until we look. And Mars rewards those who look carefully, who ask good questions, who follow the evidence wherever it leads. It has for decades now, revealing itself layer by layer, mystery by mystery, discovery by discovery. So as we conclude this journey across the Red Planet, as we've explored these 10 remarkable findings that challenge and inspire us, remember that this isn't the end. It's barely the beginning. The story of Mars is still being written. The greatest discoveries might still be ahead of us. The answers to our deepest questions about life, about planets, about our future might be waiting there in the rust-colored dust, under the pink sky, on the world that has fascinated humanity for thousands of years and will captivate us for generations to come. Mars is calling. Can you hear it? It's in every image sent back by the rovers, in every new discovery announced by scientists, in every plan for future missions. It's calling us to explore, to discover, to understand. And one day, perhaps sooner than we think, we'll answer that call. We'll send our ambassadors, our explorers, our pioneers to that distant world. And when they arrive, when they take those first steps on Martian soil and begin to unlock the planet's remaining secrets, we'll all share in the triumph, the wonder, and the knowledge that humanity's story now includes 2 worlds. The question isn't whether Mars has more secrets to reveal. It does. The question is whether we have the courage, the curiosity, and the determination to uncover them. Based on everything we've achieved so far, on the spirit of exploration that took us from caves to cities, from horseback to the moon, from wondering about Mars to driving rovers across its surface, I believe we do. Mars awaits. The next chapter is ours to write. What will we discover next?